So dispersion, this is going to be a short one, but certainly it's very, very important. Dispersion is basically the term that we use to describe the fact that the index of refraction is different for different wavelengths for most media. And what this means is, essentially, as we see with the prism, the angle of refraction will be different for different colors of light because basically the different wavelengths or frequencies create a different response from the atoms or the electrons within the material. Okay, let's talk about what's going on here with dispersion. Again, this is the idea that the index of refraction changes as a function of wavelength. All right, so, all right, again, if we have light traveling in a vacuum, essentially we have all the waves propagating at 3.0 times 10 to the 8 meters per second. All right, doesn't matter if they're radio waves, doesn't matter if they're microwaves, infrared, visible, ultraviolet, X-rays, gamma rays, all of them propagate at the same speed. However, when we come to a transparent medium, there's going to be some interaction. After all, these are electromagnetic waves. You have oscillating electric fields and magnetic fields. There's going to be an interaction between the electrons of the atoms and molecules and the wave as it passes through. Now, in the classical picture, we think of the electrons or the atoms or the molecules as being essentially little oscillating dipoles. And they're going to have a resonant frequency. They're going to have a frequency at which they like to vibrate. So when red light passes through a transparent medium, if it's far from a resonance, a place where that atom or molecule likes to absorb energy, it's going to have less of an effect because the red light being away from the resonant frequency is not going to create as strong as an oscillation as, say, blue light, which might be closer to the resonance. Okay? The closer you are, and this is going back to forced harmonic motion, the closer you are to a resonant frequency, okay, with some driving force, oscillating driving force, or light wave is our driving force here. The closer you are, the larger the amplitude of the oscillator is going to be, and the greater the secondary waves are going to be. Remember, the index of refraction, the fact that we slow down light, so to speak, with some transparent medium, comes from the fact that the primary waves, as they go through, set up secondary waves from the atoms and molecules, which creates a phase delay. Okay. Here is basically a pretty good representation of what we would get in, let's say, glass. It's oversimplified because in glass, in water, there are many, many resonances. These all correspond to different types of ways that the transparent medium can absorb the energy. In the infrared, it tends to be vibrational modes. In the microwave, it tends to be rotational modes. In the ultraviolet, it tends to be electronic modes where the electrons go from one energy level to another. But let's keep this really simple and say that we have one absorption line in this entire medium, and that's sitting somewhere in the ultraviolet. So that black line right there represents where the medium is going to absorb almost all the energy that comes in. We know, in fact, that it's difficult to get a suntan through a piece of glass because it absorbs ultraviolet light pretty well. You know, most crown glass absorbs ultraviolet light. Quartz glass does a better job of transmitting ultraviolet light. So here is our resonant frequency. What that means is the atoms in this glass really like to resonate, really like to vibrate at these ultraviolet frequencies, but they'll still vibrate at some other frequencies too. Now, when the light comes through, and let's say that it's in the red part of the spectrum, okay? we're really far from this resonance. And what that means is that that red light's not very effective in making these electrons vibrate back and forth. Okay? So red light goes through there. There's not going to be a lot of interaction between the light that's passing through and the atoms themselves, and therefore there's not much of an index of refraction. Okay, it's not very, very great, that index of refraction. But as we get closer and closer to this absorption line, this resonance, okay, let's say that we're now in the violet part of the spectrum, right here. There's going to be a huge reaction. We're very close to this resonance. There's going to be a huge reaction. And notice what happens. We go from a moderate index of refraction to a much higher index of refraction as we go to a shorter wavelength. Okay? And, you know, I don't want to go into too much detail in the classical picture of a forced harmonic oscillator, but, you know, generally what happens is at a frequency, at a driving frequency lower than the resonant frequency, we get these delays and n becomes greater than 1, okay? As we get close to the absorption line, it doesn't really matter because almost all the light's being absorbed anyway. But actually, on the other side of the absorption lines, you can get a less than 1 for index of refraction. But, you know, we want to keep this as simple as possible. And, you know, basically say that dispersion is due to the fact that we can be closer to a resonance, usually at a higher frequency, or further from a resonance, and that is going to create different indices of refraction, okay? It also sort of explains why flint glass has a higher index of refraction than crown glass, okay? We're putting in different materials which are going to have stronger resonances in that violet edge or ultraviolet edge of the spectrum, and therefore we're going to get a larger interplay between the incoming light and the secondary waves that the atoms produce. So here we can see this. Here's our borosilicate crown glass. You know, usually with most ordinary glass, it's potassium glass. But here you can see we're using boron, same effect, low index of refraction as far as glass goes. Not a huge, let me use a different tool here to sort of show this. You know, from the violet end to the red end, there's not really a big change in the index of refraction. So we'll say that crown glass doesn't really have a very large dispersion. We go to flint glass, and definitely there's a larger dispersion. There's a much greater change in the index of refraction from red to violet in flint glass than there is in the borosilicate glass. And then these extra dense flint glasses, or dense flint glass in this particular case, where we're using titanium, you see a very, very large dispersion, very large change in the index of refraction. And this large change in index of refraction is used to an advantage. It's used to basically disperse the light. So, for instance, stemware, which is made out of flint glass and extra dense flint glass, this cut, what we call cut crystal, even though it's a glass. I don't know where all these terms come from, but by creating facets in it, creates little prisms. And the more dispersive the material is, the more it spreads out the different colors and produces this prismatic effect. So if I were making a prism out of these materials, I would not make it out of borosilicate because you're not going to get a very, very large spread in the angles. I want to make my prism out of something like dense flint glass, you know, something with a lot of titanium, rutile, a lot of lanthanum, something that's going to make it very dispersive so it can spread the light out very, very well. And again, here you can see that effect. Here we have a prism, and we know that the index of refraction is higher for violet light than red light. And just go back right here. Here's the index of refraction for red light. Here's the index of refraction for violet light. We jumped from 1.7 to 1.71 to about 1.8. So clearly, the violet light is going to be bent more. And we can see here, white light comes in. We have the violet and the blue light bent the most. And then we have the red light at a lower index of refraction is not bent as much. And that creates this spreading out of the colors that we know as this prismatic effect. Okay, so that is how prisms basically work. Newton was aware of this, that white light could be broken into the different colors. He also did something quite interesting. He took two prisms. He would break the white light into all its colors, and then he would put it back together. And this was important for his way of thinking about light. He believed that light was made out of particles, and that his reasoning for this is that the prism would act sort of like a sorter, would sort out the different colors. And if the light was made out of particles, that would make more sense than something physically sorting out, different waves. And again, here we can see the effect of the prism. The reason why the prism is shaped the way it is because we want two refractive surfaces at different angles. So here is the normal to the front surface, and then here's the normal to the back surface, based on what color of light that you're sending through here. And clearly the angle of incidence is going to be greater than the angle of refraction on this first interface. You can see the red light separates from the blue light here. And then at the second interface, you're going to get even more of a separation as you go from higher index of refraction to lower index of refraction. Now, this becomes the basis for a spectrometer. The prism spectrometer was first used to take a look at the spectra of different emission lines or absorption lines. And this allowed us to understand, later on we'll see, it allowed us to understand the structure of the atom. Bohr's model of the atom was very, very important in terms of the development of quantum mechanics. But now most optical spectrometers, most spectrometers that operate in the visible as well as the infrared and ultraviolet, replace the prism with a diffraction grating. And the reason is that a prism is only transparent in the visible part of the spectrum. Well, I mean, you could use quartz, but it's not very dispersive. Whereas a diffraction grating, we'll find out, we can use that or design it so it can operate almost at any frequency with the proper setup. So again, spectra, using a dispersive element like this to break up the light into its different frequencies has been very, very important in determining not only chemical composition, but why the atom behaves the way that it does. Now, rainbows. Rainbows are a phenomenon that we see usually when we have precipitation. It should be emphasized here that I don't know if you're aware of something called a sundog, but a sundog, which is usually associated with a 22 degrees halo, occurs when ice crystals disperse the light. So we can actually see the same prismatic effect in cirrus clouds, which have ice crystals. But the rainbows are, the most popular type of dispersive halo. And the rainbow as you can see here, breaks the sunlight into different colors, but you may not be aware of how it does this. Well, the first thing we have to accept is that raindrops do not look like teardrops, okay? That is when we have water dripping off of some object, and as it's about to fall, it stretches into this teardrop shape, okay? Raindrops are actually spherical, okay? And that's due to the surface tension of the water. The water wants to pull itself in a sphere. Larger raindrops can become oblate spheroids due to air resistance, but basically they're fairly spherical in shape. So as the rain is falling, it is going to act like a prism. It has multiple surfaces which refract and reflect the light, or I should say it has one surface. There's going to be instances of refraction and reflection. For the bright part of the rainbow, it's a single reflection off the back of the raindrop. Sunlight comes in, it breaks into its different colors. Red is less dispersed than violet. And then when the light leaves the rainbow, it is the red light which is angled down the most, whereas the blue and violet light has the least angle. And this doesn't want to draw. Okay, I'm drawing blue on blue. That's not really effective. But if we reconstruct this and look at this, where the red is at a greater angle, when we look at the falling rain reflecting the sunlight back to us, the red is on top because basically at the more shallow angle, we are going to be looking at higher raindrops in the sky, where the violet is different. And that's exactly what we see right here. We are looking at a rainbow. When we look at the top of the rainbow, we are looking at the light which is being refracted by the raindrops, where the red is aligned with our eye. And the bottom, of course, that angle is aligned with the violet light. So, you know, I guess we consider this an optical illusion. It looks like the rainbow is physically sitting there, but in fact, it is all the raindrops that are, you know, behind the sunlight and refracting back to your eye. It's actually possible if you're at a high enough altitude. You're just seeing an arc typically when you're on the ground. At a high enough altitude, you can actually see the rainbow go all the way around. There's also secondary parts of the rainbow. Here you can see the primary rainbow, and then you can see secondary rainbow, which is reversed. And the way that this happens is the light comes in, refracts off the surface, bounces off the back end twice, and then to your eye. It's much dimmer because you have two reflections here. And every time you have a reflection, you also have some of the light making it out. So with two reflections, it's certainly a lot dimmer than a single reflection. Okay, well, that's it for dispersion. And again, dispersion, essentially what's happening here is that for different frequencies of light, if they're closer to a resonance, we generally get a higher index of refraction because the secondary waves are more intense, you know, in terms of what's created by the atoms. Farther away from a resonance, we tend to have a lower index of refraction. And again, really most optical media that we use, that index of refraction is really mostly due to resonances that are outside the visible part of the spectrum in the ultraviolet.